we're going to have a go at calculating values for gravitational potential energy and kinetic energy and combining them, using the law of conservation of energy to combine them, to calculate one or the other of the factors within those equations. So let's start with a question on gravitational potential energy. Here's a nice straightforward one. We have, let's call it question 1, a 5 kilogram box, so obviously that's the mass, gains, so it's going to obviously be lifted up, 25 joules of GPE, so that's the GPE, and then it says calculate the height of the shelf. So we want to find out how far it has been lifted up. So here's the box. It's going up by however high the shelf is onto the shelf at the top there. The box has a mass of 5 kilograms. So that's the basis of our question, so let's have a go at it. As always, we start with the equation. GPE is equal to mgh, which we learnt in the last video. Now we want to find h, so we want to rearrange this equation to give us h. So to do that, we have to get h as the subject to the equation, and because it's multiplied by mg, we're just going to divide both sides by mg. It's going to cancel out on that side to give us h is equal to GPE divided by mg. Okay, now the GPE is one quantity, it's not G times P times E, it's just the gravitational potential energy. And that's given in the question, so we have a value of 25 joules, and the box has a mass of, the box has a mass of 5 kilograms, and then we just need to know what the value for gravity is. Now we're assuming this shelf is on Earth, so if you remember, the value for gravity is 9.81. So all we need to do is calculate that, and that will give us a value for the height of the shelf. And when we do that, we get 25 divided by 5 times 9.81, which gives us a value of 0.05097. I'm going to round that to 0.51. So 0.51. And because everything's in standard units, joules, kilograms, etc., that's going to be in meters. So 51 centimeters or 0.51 meters off the ground, or higher than wherever it was when it was when it was lifted. Okay, so that's one for gravitational potential energy. Question 2 here is for kinetic energy. It's a nice straightforward one. A cricket ball of mass 0.2 kilograms, so that's the mass, is thrown at 12 meters per second. So it's meters per second, that's got to be the velocity. And it says calculate its kinetic energy. So its kinetic energy is equal to a half times the mass, nearly wrote the number in there, times the square of the velocity. So half mv squared. So putting the numbers into that one, the kinetic energy is equal to just that half, which we can use 0.5 in the calculator, times the mass of the object, which is 0.2, we're in kilograms, so that's okay, times 12 squared. Never forget the squared. Quite easy to, when you're transposing this equation and substituting the numbers in, to forget the square. To make sure that you square that, and then we just need to calculate that. So let's use our calculator again. The half is just 0.5 times the mass, which is 0.2, times 12, where are we? Squared. Let's put the bracket in there. Whoops. Let's start again on that one. Learn to use my calculator properly. 12 squared. There we are. Gives us 14.4. Probably could have done that in my head, knowing that 12 squared is 144. So 14.4 joules of kinetic energy. And the only thing to remember, as I just said, is make sure you remember to use the square. Okay. All right, so that's one for kinetic energy. Question 3 here is about a drone. So a drone of mass 2.5 kilograms is flying at a height of 25 meters, that's h, above the ground, at a speed of 20 meters per second, v. So we've got a mixture of quantities here, some that relate to gravitational potential energy and some that relate to kinetic energy. So we're going to take them one at a time. Calculate its kinetic energy. Well, the kinetic energy is just going to be half mv squared again, which is going to be a half times 2.5 times the square of its velocity, 20 squared. If I can use my calculator successfully this time, we have 0.5 times 2.5 times 20 squared. And that gives us a value of 500. So the kinetic energy of the drone is 500 joules, flying at that speed. And the gravitational potential energy, or the GPE, is mgh again. So that's just equal to the mass of the object is still 2.5. The gravitational field strength on the Earth, 9.81, multiplied by the height, 25. And when we multiply all that up, we've got 2.5 times 9.81 times 25 gives us 613.125. So I'm going to keep it at 3 significant figures, although I probably should round it down to 2. 613 joules. And then it says, what is its total energy? Well, the total energy is just equal to the sum of all its different energies. And assuming there are no other energies that we haven't thought about, that's just going to be the value of the kinetic energy plus the value of the gravitational potential energy. So that's going to give us, 1,113 joules in total, just adding these two numbers up here. Okay, so that's a typical question combining those two. Those are reasonably straightforward questions. The next one is harder, and this would probably be worth 4 marks or so in an exam, this next one. So question 4, if a highboard diver of mass 50 kilograms jumps off the 10-metre platform, how fast will she be going when she hits the water? So we have a platform which is 10 metres above the ground, and we have this diver who jumps off and hits the water at a certain speed, which we want to find. How fast will she be going? That's what we need to find out. So, we need to combine our equations for kinetic and gravitational potential energy here again. The mass is 50 kilograms, and the height is 10 meters. So we can easily calculate GPE straight away. So the GPE is equal to mgh, which is equal to 50 times 9.81 times 10. So when we multiply that out, we're just going to do it quickly. So that's going to be 500 times 9.81, so that's going to be 4,905. Now, how fast will she be going? If we think back to our ideas about energy conservation, the total amount of energy is always conserved. It's just transformed into from one type to another. So up here, the diver has gravitational potential energy. As that is lost by moving downwards by that change in height, the diver will speed up. Naturally, she'll accelerate due to gravity. And that's because all of her gravitational potential energy is being gradually transferred into kinetic energy. So by the time that she hits the water, all of her energy is kinetic energy. And because of energy conservation, and this is a point that a lot of people miss, if she has 4,905 joules of gravitational potential energy up here, she will also have 4,905 joules of kinetic energy down here. Because up here at the top, she has 0 kinetic energy, and therefore all of it was gravitational. And down here at the bottom, she has 0 gravitational potential energy because it's all been lost in her fall, and therefore all of it must then be kinetic energy. So effectively, the change in gravitational potential energy as she falls is equal to the change in kinetic energy that she gains as she falls. So the change in gravitational potential energy is effectively a loss of 4,905 joules, and the kinetic energy is a gain of 4,905 joules. So she has the same kinetic energy when she hits the water as she had gravitational potential energy at the top. So in order to find her speed, we already know her kinetic energy and her mass, so we can find her speed easily from that. So the kinetic energy is equal to a half mv squared. Now I'm going to rearrange that one step at a time. It's probably easier to put the numbers in at this point, but I'm going to rearrange it algebraically so you can see how to do it. So because there's a half in there, we need to multiply both sides by 2. So 2 times the kinetic energy is going to be equal to mv squared. And then we need to get the v on its own, so we're going to divide by the m. So 2 times the kinetic energy over m is equal to v squared. And the last step is to take the square root of both sides, which is going to give us v on its own. I'm also going to flip the equation at this point. So v is equal to the square root of 2 times the kinetic energy divided by the mass. And then it's just a case of plugging the numbers in. We have V is equal to the square root of 2 times 4,905 divided by the mass of the diver, which is 50 kilograms, and therefore the velocity of the diver when she hits the water is the square root, oops, hang on, let's just get rid of that one, my calculator playing up again, the square root of, let's do 2 sets of brackets, 2, oops, that's 3 sets of brackets, sorry, 2 times 4,905 divided by 50, close the second bracket, and there we have 14, almost exactly 14. So we're going to say that the velocity of the diver is 14 meters per second. Okay, so that's how you do that one. That's a 2-step calculation, but there is a quicker way if your algebra is up to it. And the way to do that is to take this equation and substitute the actual equations for those two things. So gravitational potential energy is mgh, and you can actually set that equal to a half mv squared algebraically, and then rearrange that entire thing for velocity. Don't worry if this is too much for you. The first method is fine, but actually this way is much quicker. And actually the mass is the same, it's the mass of the diver, so these m's cancel out and disappear, leaving you with gravitational field strength times height is equal to half v squared, and from that it's quite easy to rearrange for v. Okay, so that's quite a challenging question on the conversion of gravitational potential energy to kinetic energy.